So this was the adiabaticity approximation, and what can we learn from it? But what happens if the potential energy surfaces we had in this picture actually not that far away from each other, but may cross? So this is a situation which you may find in many cases as well. So you have crossings here. So if you are interested only in atomic positions somewhere here, you can ignore this first excited state, potential energy surface. However, in many situations, especially in the case of chemical reactions, when you would like to consider a transition from this minimum into this one, you have to take account of this crossing of the potential energy surface. And therefore, you have to consider in more detail what happens here. Um, if in the adiabatic approximation we only had to consider a single term in the expansion of the total wave function, this time we need to consider two terms. So in that case corresponds to taking in this our original expansion of the total Schrödinger equation wave function only two terms for zeta equal ground to the ground state and the first excited state, which are closest to each other. In that case, our equations for the nuclear wave functions Xc1 and Xc2, there will be two of them in that system of equations. There will be two equations here, which one need to solve together. And this is a rather difficult thing to do. So a lot of approximations and different methods being developed to do this kind of job. But importantly, what you find after solving these equations, then you leave this degeneracy here at the crossing, and you would have the potential energy surface of the ground state having this double minimum, and the potential energy of the excited state lifted up, creating here a little kind of opening, a gap. So then transition of the system from the ground state to this another minimum can be considered as happening on the ground state potential energy surface only. I just mentioned to you because you may come across in the literature, there's another approximation which is called diabatic expansion, or a Born-Oppenheimer approximation. In that approximation, a slightly different expansion of the wave function is used. If before, let's have a look again at this expansion here to understand the difference. If before we expanded the total wave function with respect to electronic wave functions, and this capital R was the same as in the wave function we're interested in, even though we made this approximation, this chi wave function, a nuclear wave function, would still depend on these atomic positions, the capital R. In the diabatic expansion, the psi wave function, the electronic only wave function, is taken at the minimum of the potential energy surface for each particular electronic quantum number. We can still do it because these wave functions still form a complete set of wave functions, because they are obtained as solutions of the Schrödinger equations for the electrons. But instead of considering it as a function of the nuclear positions, we take just one nuclear position. In that case, these coefficients would depend on the R. They would acquire the full dependence on their nuclear positions. In that case, one can also obtain the equations for this nuclear wave functions. They will be different from the ones I gave you above. And this expansion is also exact, of course. And the approximations which are made are only in how many terms in this expansion you would take. Equations are much simpler in this case because these wave functions do not depend on nuclear positions. And it's a good exercise to actually derive these equations. So this is another method which sometimes is used because it's a little bit easier to handle mathematically.